emails. This is AI in action, right? Social media messages, comments, right? Comments everywhere, right? Social media comments, Instagram comments. What else? Medical reports. Medical reports is kind of text plus numerical data type of things.
So journals, articles.
Yeah, product reviews, yes. Yes, research papers, news articles, correct? So there is enough amount of text data. All of us also communicate with language. So it's important, right? I mean, if you are not learning how to process the text data, then there is a severe problem because a lot of data seems to be in textual format. Okay, sometimes this data is referred to as unstructured data, right? Text data is a class of what is called unstructured data. Other unstructured data sources are images, videos, okay, and there is other form of data which is structured data, or table structured data, right, where there is a fixed schema, or number of columns in the data, right? So these are two broad categories of data, right? These are two broad categories of data. The unstructured data and structured data. Now we know that machine learning algorithms expect data in numerical vector form, right? So we need to convert unstructured data into numerical vectors, correct? And it's very interesting to know that each of these, how do you convert these unstructured data of one form into the numerical data? There are fields, there are dedicated fields of study, right? For example, if you have language data, if you have language or text data, you want to convert that into, let's say, numerical vector. There is a field of study called NLP, or natural language processing. Natural language processing, which basically studies how do you effectively represent text in form of numbers. Correct? If your images to numbers to numerical vector or features, there is a field, right? You can call it as computer vision or image processing. And a video is nothing but sequence of images, correct? So it is also covered inside this. So video is nothing but sequence of images. There is one more unstructured data, which is audio data. Audio data. So if you have audio data, we also convert audio data into some form of numerical features. And there is a field for that, which is called speech processing. So these are fields in themselves, right? I mean, so these fields mainly decide how do you really come up with the effective representation for text or effective representation.
Sir,
Yes.
sir, there are electrical signals and those sort of data also, right?
Yeah, but I mean, in what? Yeah, there could be those type of data, but those electrical signals are already in numerical format, right? So sometimes they may be in numerical format, or you may have some kind of an image representation. Then you have to take that image representation and convert it into numerical format. Okay.
Yeah.
All right. Got it. So what we are going to do is we are going to, because we are into introductory course, we are going to talk about simpler technique of representing text and simpler techniques of representing images, right? So let's look at those simpler techniques, and I'll also tell you what are advanced techniques of doing these things. And then, I can point you to maybe some resources or whatever, or when you do deep learning course, you will get more exposure to some of those ways of representation. Okay. So right, in machine learning what we do. So we have, let's say, text data. Then we are going to have some kind of a representation. And then we are going to apply ML, machine learning technique on that, right? And then you will get maybe output, right? So representation is where we will be focusing in today's class. Okay. Is this clear? All right. So before doing anything else, let's dive directly into the code and let's write code. I'm going to share, this doc as well as collabs with you later, but it will be great if you can actually code along with me so that, you feel you basically get better experience and better learning outcome of this. Okay. So let's start with, how do you really represent text? Any questions so far? Any questions from anyone? Happy to take it because we are going to dive into the code directly now. Okay, before that, maybe we should do this, right? What are typical tasks? What are typical tasks that we are interested in addressing with text data? What are typical tasks? Okay. So, you see reviews, right? What do you do with reviews? You read product reviews. Let's say you're going to buy some product from Amazon. You go to product review page, you read reviews. And what do you decide? You decide whether this review is good or bad, right? You get to know what is the sentiment of the review, right? So you can get sentiment analysis, which is again a classification problem. Where we mark review as positive or negative or neutral as well, right? You can have multi-class classification problem here as well. Okay. You must be doing this with movies and things like that, right? Then, in email, we do spam email filtering, right? Again, you don't like to see spam emails, right? So we already have in Gmail, if you are using Gmail, there are spam filters already there. So spam email filtering is a classification problem. Where we classify email as spam and not spam. Is this clear? What other problems do we have? So sometimes from product reviews, product entity extraction, right? You want to extract product entity or product features, right? Product feature extraction. This is like entity extraction. So let's say you want to buy a
Like
camera.
or a book
Sorry?
or something like that.
Sorry?
We need to learn if it's a book or electrical item or something like that.
Yeah, that's a classification problem at a product level itself. But let's say you are interested in buying a mobile phone, right? Then you go in the product review, you check for specific what features are mentioned in a review, right? Whether they talk about a camera of a phone, whether they talk about the battery life of the phone, whether they talk about the display of the phone, whatever, right? So display, storage, battery life, right? These are product attributes, and you want to extract these product attributes, right? So this is in general called as entity extraction problem, where you are trying to So this can also be thought of as a classification problem. Classification problem, where every word in the review is being classified as a product attribute or something else, right? It's not a product attribute, that type of thing. So this type of entity extraction also happens in news, right? So if you're doing news, if you're reading news, you typically find out what is this news about, correct? So first could be, let's say, so news classification. Let me write this. News classification. So you want to classify news into types, let's say. So it's a classification problem where a news is classified into predefined classes. Example, political news, sports, entertainment, and so on. Getting it? So I have listed down some of the tasks. Is this clear to you? Any questions?
Yes, sir.
Yes, please go ahead. Okay, it is clear, right? So, okay.
I mean, there can be many such problems, but we
Yes.
don't know. We can know about this at problem at hand.
Yeah. So I have listed down some 4 or 5 problems. There could be more problems based on the text. You can also do text clustering, right? If you have a bunch of text, you want to cluster it into, let's say, good reviews, bad reviews type of things, that could also be possible. Yeah, there could also be many other interesting problem under text. Okay. So think of these as representative problems. This doesn't cover all the problems that we encounter as text problem, but fundamentally, right? I mean, machine learning problems, we have already seen the, taxonomy of machine learning problems, right? There is regression problem, then there are classification problems, or there are clustering problems, correct? So supervised, unsupervised, regression, classification. Within classification, we have single label classification, multi-label classification, single class classification, binary classification or multi-class classification, correct? So the same kind of thing applies here, because ultimately text is nothing but some kind of a data on which we want to do learning, right? So nothing changes as such. All that we are now going to do is we need to somehow represent this text into form of numerical features, and then we can go on applying machine learning algorithms as usual, right? Once you convert text into numerical features, our job is done, in a sense that representation is done. Then rest of the machine learning algorithms, right, the way we are applying it on the numerical data, in the same format we'll apply them. But there are some very interesting things that we will learn on the way while learning this representation. Okay. So enough of discussion. Let's get into the coding and see how this works. Okay. So I'm going to share my tab. So I have already, full disclosure is that I have already worked on these collabs, and I'm actually using them as reference while I code. I have done this because I want to make sure that I don't do too much of experimentation on the go. So I already have some reference collab which I'm going to use, and I'm going to type from that collab. Okay. We are going to first use count vectorizer. So we will first import count vectorizer from sklearn. Where is count vectorizer in sklearn? It is in feature extraction dot text. sklearn dot feature extraction dot text, import count vectorizer, and I will share my original notebooks with you after this class. But I'm thinking of coding along with you, so that you get to learn more and you get more time to think, right, when we code. Whenever the material is already ready, instructors tend to move fast. So I want to deliberately slow down. That's why I prefer writing in a doc, so that it gives you some time to think about what we are talking about. The same thing I'm trying to do it with Collab. Okay, I hope the speed is okay with you, and you're not bored with this approach. Okay, let's connect. You are familiar with Colab, so you know that. So connect to this Colab and execute this line. Okay, so count vectorizer is already here. And you already know, right? I mean, if you do question mark count vectorizer, you will get documentation of count vectorizer in the right hand side. Right. So what count vectorizer does? Count vectorizer converts a collection of text documents to a matrix of token counts. So let's take an example. Right. Count vectorizer itself will have an example. So we can straight away try that example. Instead of reading some file, right? Let's take a toy example. Let's use this corpus in count vectorizer. Okay. So they have defined a corpus, which is a vector of strings, right? Or an array of strings. So let's use this array. I'm saying corpus equal to we don't need this copyright. So let's write this. So we'll write exactly what is here. This is the first document. You can also copy, not a problem. This is the first document. This document is the second document. Okay. And this is the third one. Is this the first document? Question mark. Okay. Now we have defined our corpus. So we have corpus which has got 4 strings, and we basically want to convert these strings into numerical representation. So let's first apply count vectorizer and then come back and understand what it does. So count vectorizer is a transform, right? And you know how transformations work in sklearn, right? So we are going to define a count vectorizer. So vectorizer equal to count vectorizer. We are going to use default count vectorizer with default parameterization. Right? So we are going to initialize a count vectorizer object with all default parameters. Okay, so I initialize this. Now what we are going to do is, so there are 2 things, right? This is a transfer, this is a transformer, right? This is a transformation object. So what we need to do is, we need to first learn the vocabulary, right? What all words are present in the corpus. So that happens with the fit function. So if you call just a fit function, it will basically learn the vocabulary of this corpus. Vocabulary means what all words are present in this corpus, right? And there could be some words that are not present in this corpus, and we'll see how it handles it later. Okay, now you have defined this vectorizer. Now what we are going to do is, we are going to basically do, we'll first learn this, right? So this is a vectorizer. We say vectorizer dot fit, and we'll give a corpus. So if you do just fit, it will learn it. And if you do fit underscore transform, it will first learn the vocabulary, and it will also transform the corpus into a numerical format. Okay, let's call it as capital X. And let's learn this. Okay, now this vectorizer is already trained. This vectorizer has learned the vocabulary of this corpus, and it has transformed this particular corpus into a numerical representation. So let's first understand what all what all words it has learned and it has kept in its vocabulary. So you can simply call, again, I'm taking it from this vectorizer dot get feature names out. So this will get you the vocabulary. Okay? So it has said that and. So these are the words it has done. This is in alphabetical order. So and document first is one, second, the, third, and this. So these are different words. So you can see that this is there, is there, the is there, first is there, document is there, correct? Then second is a new word from the second sentence, so that is also covered here. Then third is the word, and is the word. Both the words on the third ones are also covered. And the last sentence does not have any new words apart from what it has already seen. So there are how many words? 1, 2, 3, 4, 5, 6, 7, 8, 9 words are there. Correct? Now what we'll do is we will basically print this array, right? This X into array representation. Okay, so this is a this is a function. So now you can see that this is the representation that it has learned. Let's try to you may not like this kind of representation, so let's convert this into basically in the data frame format. Okay. We'll convert this into data frame format. So how do you do it? So we say, let's first import pandas. Import pandas as PD. Are you coding along with me?
Yes, sir.
PD dot data frame. Okay. So PD dot data frame, we give this x.to array as input, and names of the columns are names of the features. Okay. Now you see that. Okay. What is the first sentence? So first sentence is, this is the first document. So you can see that this is the first and document. So there is one for those columns. So these are the counts, right? So in the first document, the word document appears 1 times. First is and they also appear 1 times along with this. But the words like and, 1, second, and third, they don't appear. So there is 0 for the corresponding cells. In the corresponding cells, you see 0. Are you getting it? In the second document, this document is a second document. So you can see that this is appearing 1 times, document is appearing 2 times, is appear once, the and second appear once. So you can see that document appears 2 times, is, second, the and this, they appear once. Are you getting this? So this is the format. So now what happened with this? We are basically representing each string with the words, correct? But we are not taking into account the word order. Are you getting it? So let's write it down. The each text string in the corpus is represented with the words present, by ignoring the word order. Is this clear? So this representation is formally called bag of word representation. Bag of word representation. Getting it? Is this clear? Is this clear to everyone? Any question?
Yes, sir.
Everybody is up to this point in the coding journey? All right.
Yes, sir.
Okay, so you can once check, right, all the parameters, some of the important parameters, right? Now what happens is that the text is not in a clean format, right? Sometimes, some of these words like this is this, the T of this is capital, and this is in small case. So this is like capitalized and this is in small case. So we need to basically, both these words should be treated in the same way, right? So we need to convert each word in the string into lowercase, and this is, I think, done by default. So there is a lowercase parameter, lowercase. By default, it is true. So what you can do is you can instantiate this count vectorizer where lowercase equal to false and check it out. Can you check it out? So this is your experiment. Okay, what is the experiment? Experiment. Instantiate a count vectorizer with lowercase equal to false. Put this parameter lowercase equal to false and observe the document term matrix. So this X that you see here is called document term matrix. This is a document term matrix. This is a document term data frame. So on columns you have what is called as the terms, and on rows you have documents. So this is zero document, this is first document, second document, and third document. Now we have, these are strings, right? These are short strings. If you have long documents, each document will be considered as a single entity, right? Each document is a row, and what you have on the columns are entities. Could you do this? Could you quickly write the code and explore this? So I'll just come back. I'll have some water and I'll come back. Okay. So take a couple of minutes and complete this experiment. So I'm back. Did you try this? I'll also try.
Yes.
What is the change now? How many? So let us write the code here. So lowercase. So here you say lowercase equal to false. Okay, maybe small false.
An additional feature is added and then distributed based on.
Exactly. So you should check out the feature names out, right? That is the most important part. You should check out that. So this F has to be capital. You can see that now there are case sensitive features, right? So this and A is capital, is capital, this is capital. So you can simply print the length, right, of this array. Right? Earlier we were having 9 features, right? So now what you can also do is you can construct a data frame like this here. Number of features. You can see number of features are 11, and these are the 11 features. Are you getting it? So lowercase equal to should ideally be true. Okay, so I actually made you make it false so that you get to experience this particular issue. Clear? Is
Yes.
it clear?
Yes, sir.
Okay. Now, second interesting thing is we also need to figure out, right? I mean, what do you do with punctuation marks? So there are some punctuation marks here. There is question mark here. There is full stop here. So we have not seen that they're getting added here. And this is happening because we have a specific token pattern. So we have a specific token pattern, and this token pattern only considers words that are more than which are at least, these are the words which have length of at least 2. Okay, so this is a pattern that they have. So you can also change this token pattern. So if you are working in some specialized domains where there is a slightly different token pattern, you can specify that, and that's how your words will be. That's how your tokens or your words will be decided. Right? So the way these feature names are decided is because of this particular token pattern. Getting it? So if you change this token pattern to something else, you will start seeing even punctuation marks in this token pattern. Okay, is this clear? So you can actually try to also play with this token pattern. And okay, so that's another thing. So can you actually play with a token pattern where you can include the punctuation marks as well? So let us try. I'm going to try. So currently token pattern is this, right? So let us copy this token pattern. Okay, so let's say lowercase equal to true, and we specify the token pattern, and we make token pattern as the default token pattern itself. So this token pattern also understands Unicode character, meaning if you have text in Indian language and other things, it will recognize it because we have U here. That's the Unicode character thing. Right? And I'm also going to include some kind of let's say punctuation marks, something like dot. Let me see if it works. It is not working. Empty vocabulary. Okay, I think I made a mistake here. I'm including, let's say, not words also. Let me see what happens. Empty vocabulary, product document contains stop words. But we are not doing it. Let me try some other token pattern. It's not working out. Let us see. Okay, so I'm going to try a token pattern which is simpler. So where are we? We are here. Okay, so we are going to try A to Z and capital A to Z plus. So we'll only allow more than one word, one word token. So we get to see this. Now there are 9 features here. If I want to include also, let's say dot in this, let me see if this works. So now you can see that 1 and dot, this is getting captured here. Right, so this was our thing, right? So 1 and dot, for example, is getting captured. But we have not added this, right? So if you also want to add something like question mark, I'm going to add question mark in the allowed character set here. So you will also see question mark getting added. You see it? Is this clear? So this is about regular expression. Do you know how to write regular expressions? I'm sure you learned it in Python.
Yes, sir.
You learned it, right? So you can write appropriate regular expressions and get words extracted. Okay, so I'm going to remove those punctuation marks from the character set, and you will just see the original 9 features. Okay, There is one more problem, right? I mean, sometimes there are certain words that are not that informative, right? Words like the, is, and, this, right? They appear in all kinds of documents. So they do not tell you much about what that document is talking about, right? So these words are called as stop words in English. Okay, these are called stop words. And what we need to do is we need to basically get rid of these stop words from the document. And this is a very standard step in the text processing. And we don't need to code this, right? In count vectorizer, we have a way to basically eliminate these stop words. So there is a parameter called stop underscore words, and by default there is no stop word list, and this is a list, so we have not specified any list. But if you specify English here in stop words, so a built-in stop word list for English will be used here. Okay, so let's try to remove stop words. So let's say remove stop words. Okay, all that we'll do is we will just cut copy the code and paste it over here. And we are going to just write here stop underscore words is English. Okay, it's always a good idea to write parameters on new line like this. Okay, and let's check out. Now we only have two features. Getting it, rest of the other features got removed because they were stop words. So document and second are only two words that are remaining. So this could happen that in some domain that you are working on, certain stop words may also be useful. Then you will have to basically construct your own stop word list by adding some stop words from English and then adding some domain specific stop words. Is this clear? Is this clear to everyone?
Like here says stop word equals to English. So when we are doing this, how it's able to find like those words has to be removed?
So basically, when you say English, right, it is going to use the stop word list for English language. Okay, so we have a stop word list for English language, the default stop word list that is there in count vectorizer. It is going to use that list, and any word that is present in that list will be removed. Getting it? So you can check out.
Okay, sir.
There is this stop underscore words. Let me again check it. The stop underscore words, we can search it. Stop underscore words. Yeah, you can see it. Yeah, and you can read the description. Okay. You can also use this other list, stop underscore words. I don't know what is there in this list. We can check it out. So don't afraid of experimentation. Do experimentation. Otherwise, you will not learn. Stop underscore words. So that's why this top-down approach helps. So I think this stop underscore words doesn't exist. Yeah, I think this doesn't exist. Okay, we'll have to basically, let me go to the count vectorizer documentation G. Maybe there is some more information out there. The documentation, Control F, stop words. Yeah, I think, yeah, you can also have your own list, but currently English is the only option it seems we have, and we'll have to use it. Okay. All right, so I'm going to use English as a list, so this will not work. So English is the only option that we have. Okay. All right, so should we move forward?
I'm getting 5 features.
You're getting 5 features, that is quite strange. Did you include
document question mark?
Oh, okay. If you do this right, so I think you did not change your this particular token pattern. So I removed this dot and a question mark from here. So that's why we will get only 2 features right now. I have changed the token pattern.
Okay. Yeah. Okay. Sorry. Yeah.
Got it?
Yeah.
All of us should get the same result.
Yes.
Yeah, there cannot be any magic here because we are talking about very standard programming. There is no machine learning or AI or large language models here. A very standard program. All of us should get the same result on this corpus. Okay. What are other ways in which we can represent these documents or these strings? Any other thoughts? What are we trying to do? We are trying to represent these strings, right, in terms of numbers. So what could be other ways in which we can come up with these numbers? Yes, anyone?
We can code it CAS key or something like this.
Not really. That will be only the encoding, right?
Maybe in matrix format, matrix or something.
Matrix is already done here, right? This is also matrix format.
Yeah.
We have document of matrix already done. Can you think of some other features? So currently the features are words, right? So can you think of any other features?
Alphabets only.
Oh, so you are talking about characters? Yeah, you can also think of character thing, and there is support for that. By the way, in count vectorizer, you can also consider characters. So if you change your token pattern, right, to only one word or whatever, right, then characters will start coming. Okay, you can try that. What else? You can represent them by characters. Yes, you can see that T appears maybe 2 times, H appears whatever 2 times, I appears 1, 2, 3 times, something like that. So you're doing bag of characters basically, correct? What else can you do? So currently these characters are combined and they are words, right? We are actually cutting them at word boundary. So in the same way, we can also combine words. So you can have, let's say, 2 words, right? This is the,
Yeah.
the first, right? Or first document. So these are called bigrams where we are taking 2 words at a time and we are combining them. So what we now have is a single word, right? It is called as unigram. So you can also have bigrams where we are considering 2 words at a time. You can also
Yeah.
consider 3 grams.
Using the way the language is being spoken, we can try.
Yes, exactly. So we are trying to bring in some amount of order, right? It is not completely unordered. We are not throwing away all orders. We are at least maintaining some local order of the words, right? So you can also consider 3 grams, 4 grams. There is no restriction how far you can go, but typically people consider bigrams, right? Bigrams, maximum trigrams, 3 grams. They don't go beyond that because then vocabulary quickly explodes. So let's try, and there is a direct feature available in count vectorizer. So you can see that there is something called as n-grams. There is n-gram support directly available, n-gram range, right? So you can say the lower and upper boundary of the range of n values. So you can have, let's say, default is 1, 1. So default is unigram. If you want bigram, you can say 2, 2. So let's try this straight away. N-gram underscore range. Let's try this parameter. So I'm going to copy the same thing again, the entire thing. Let us actually include this also in this code so that you get to see, because as we are going down, we are not able to see a reference. Now I'm going to try n-gram range, right? And let's say only consider bigrams. Let's say we are only going to consider bigrams. Consider only bigrams. Let's run this. Okay. So now there are Two features. Document second and second document. This is very interesting, right? Document second is a feature and second document is a feature. But I want to know why it is coming. Okay, so now what it is doing is, okay, let us get rid of this particular argument for a moment. I will not do any stop word removal right now. And you will see that so many features. There are now 13 features for us. And this document is, first document is this, second document, the first, the second, the third one, this document, this is, this, the. Getting it? Are you getting it? Is everybody following me?
Yes, sir.
No, for me, it is document second and second document only is coming.
Yeah,
But
because your stop word equal to English is all,
English.
right? Yeah. So if you so that's why when I was doing that, I also had only two things, right? Document second, second document. So the way it does is it first removes, it will do lowercase, it will consider words and it will remove stop words, and whatever is remaining, it will start making bigrams. Correct. So you will have to first. This is fun, right? I mean, when you learn this through code, this is much more lively. You understand it much better. Is this clear? Everybody with me on this so far?
Yeah.
Cool. Now, whether 1 gram makes sense, bigram makes sense, trigram makes sense, it really depends on what problem we are solving. And we also don't want to have too many features, right? If you have too many features, then sometimes it becomes very, very sparse representation and it may not help us. So we have to carefully choose, and we can, see what parameters. We have to do experimentation and see what makes sense for a problem that we are solving. Right? So we cannot really say that only unigram will make sense or bigram will make sense.
So now for with respect to unigram and bigram, we increase the features, right? But unigram having less features. Now for this case only.
Yeah.
So in this case, we should select unigram, right?
No, we cannot say that. We have to see what is the downstream task. Let's say we are doing classification after this, correct? So we should see what kind of representation gets us the best generalized classification performance.
Performance decides the
yes, the choice of the parameter. The choice of the parameter.
Okay.
So you remember hyperparameter tuning?
Yes, sir.
So we have to do hyperparameter tuning basically on these parameters. Okay, I'll give you one example of that in end-to-end maybe class. Okay, I have those examples also prepared. I'll walk you through those examples.
Okay, sir.
Okay, now you can try trigrams as well. So you can see that number of features now. There are less features. There are 12 features of trigrams, only trigrams, right? And now what you can do is, if you want unigram, bigrams, and trigrams, you can also do that. You can just do 1,3. So now you will have unigrams, bigrams, as well as trigrams. So see what happens with this. So now we have 34 features. We have 9 features plus 12 features plus 13 features. So we have 34 features now. We had 9 unigrams, 13 bigrams, 12 trigrams. Are you getting it?
Now how we are counting, sir? How we are telling?
Okay, so let us do this, right? So let's only consider unigram. You have only 9 features.
Yes.
Correct. Now I consider unigram. Let's consider only bigrams. So 2,2 is only bigrams.
Okay.
How many features are there? 13.
Okay. 9 plus 13. Okay.
22. And if you just do trigrams like this, 3 grams,
yeah,
you have 12 more features, right? So you have now 34 features. If you do 1, 2, 3, right? You want unigrams, bigrams, as well as trigrams.
It just adds up. Okay.
Yeah, it adds up basically. Right? So typically, if I want unigram and bigrams only, I do 1,2. Is this clear? People have questions, please ask them.
Yes, sir.
Okay, I hope everybody is coding along.
Yes, sir. We are coding.
Okay. Awesome. All right. So that's about count vectorizer. Now we will move on to some other topic. So this is one vectorizer, right? So what are we doing here? We are basically counting unigrams, bigrams, trigrams, and we are recording the frequency, right? How many times the unigram or bigram or whatever n-gram appears in that document, and we store that frequency. Is that clear? Awesome. Let's move on to the next vectorizer. So I go to that. Okay, so the next vectorizer is TF-IDF vectorizer. So far we were doing just term frequency. So TF in this case, right? Let me explain this. So TF stands for term frequency, and IDF stands for inverse document frequency. Getting it? Now we are already doing term frequency. Count vectorizer basically gets us term frequency. What is the problem with that? So what happens is that, you know, term frequency is great. It tells you how many times a particular word appears in a document. But sometimes I also want to know, right, how many times this word appears across the corpus. So something like the word this. This word this is appearing in each and every document or sentence here, right? So this word is not that informative. Getting it? To some extent, this is like a stop word, right? This word is not that informative. So since this word is appearing in all documents in the corpus, this should get relatively lower weightage. Getting it? So what we are going to do in TF-IDF vectorizer is we are going to calculate TF-IDF score for every term, and that will be combination of TF, and TF will be multiplied by IDF. Term frequency will be weighted or down weighted using this IDF. Okay, that will be TF-IDF of term. So I will explain how this IDF is calculated in a scalar. TF is simple. TF is number of times term appears in a document, exactly like what count vectorizer does. Okay, and why this is useful? So this representation basically penalizes words that appear in many documents in a corpus, right? And basically the words that do not appear in many documents, they have lower IDF. Sorry, they have higher IDF, and that's why the entire product will basically go up. Okay, so let's do that. So this is inverse document frequency. Go ahead, please.
Should this be done? The modeling itself will take care of if it is not important. The model should take care.
That's a good thought. So we can also check with count vectorizer, right? But sometimes people have found in the study that TF-IDF vectorizer gives us a better representation. Okay, this is what is empirical evidence from multiple studies. Yeah.
Thank you.
Okay, so let's understand how IDF is calculated. Okay, so you have TF-IDF. So you have two things here: TF-IDF transformer and TF-IDF vectorizer, right? So TF-IDF vectorizer is basically count vectorizer followed by TF-IDF transformer. Okay, so we are going to directly use TF-IDF vectorizer. Okay, but the transformer has got good documentation about how IDF is calculated. That's why I'm going to this documentation. So you can see that IDF is calculated as log of n by df of the term. So this IDF is calculated for every term, right? And how is it calculated? It is log of n by df of the term. So in a particular document, right, what is the document frequency of this term? And n is the total number of documents in the document set.
Sir, you're writing something?
Oh, no, I'm not writing. Sorry.
Okay.
Sorry, I was not showing you the right page.
Oh,
okay, so this is the documentation of TF-IDF transformer. Okay, and the way it calculates IDF is IDF. So let us write this down somewhere in our doc, and that will be great. IDF calculation. Okay, so IDF of the term is calculated as log of n by df of the term. So let us understand what each word means. N is the total number of documents in the document set. And df of t is a document frequency of t. The document frequency is the number of documents in the document set that contains the term t. So let us write this down. Okay. I'm on my whiteboard. So where n is the number of documents in the corpus. Okay. And df of t is number of documents in which the term appears. So let's do some mental some calculation, right? So let's say there are 4 documents in the corpus, and df of term is also equal to 4. So what would be the value of IDF? Then IDF of this term is equal to log of 4 by 4. Correct? N is 4.
yeah.
df of t is 4. So which is log of 0. And what is log of 0?
Log of 1 is 0.
Sorry, log of 1. Log of 1 is 0.
0.
Correct? So this particular term, because it appears in all the documents, it gets the IDF of 0. And when you multiply the term frequency with this IDF, essentially this particular term will get the feature value of 0. Getting it? Everyone with me on this so far? We're doing some very simple calculation. Okay? So if n is 4 and df is 1, so you have basically 4 by 1, right? So which is log of 4, which is non-zero, which is greater than 0. Is it clear? So the lesser the number of documents in which a term appears, higher the IDF. Is it clear? Everyone with me so far? Okay, so let's go and do this. So I'm going to copy the whole thing again. Now we will import from sklearn feature underscore extraction dot text import TF-IDF vectorizer. And I'm going to call TF-IDF vectorizer here.
Sir, the code screen.
Oh, okay. Sorry. Thanks for letting me know. Okay, I'm going to call TF-IDF vectorizer. But before that, let's look at quickly at the documentation of TF-IDF vectorizer. Okay. TF-IDF vectorizer. Again, it also has stop words, token pattern, and gram range. Exactly the same kind of features as count vectorizer. Same arguments as count vectorizer. Okay. So what we'll do is we'll first use TF-IDF vectorizer with default parameters. And let's do this. I'm going to use the same. What do you see now? So we have number of, okay, so what did we do? This corpus is the same. This is where I made the change. Okay. This line is changed. Everything else is the same. Now my vectorizer is TF-IDF vectorizer. I basically got fit underscore transform. So it basically understands the vocabulary. It also calculates the statistics that is required to compute IDF and TF. And then it assigns the feature values which are equal to TF into IDF. Getting it?
It kind of normalizes.
Yes. In this, right, it will normalize. Let's check whether it is normalizing.
Because the values are between.
Yeah, that will happen because the values will be fractional. Because see, the log of 4. No, it is normalizing. Yeah, it is using L2 norm for normalizing. It is normalizing the way we normalize any of the vector, right? By the norm of the vector. So it takes the vector and normalizes by the norm of the vector. So if we actually change this norm parameter to none, let's do norm equal to none and change it again. Norm equal to none, for example, right? And check what happens. Yes, you see now non-normalized values.
Okay. So that is good. Normalizing, then it is.
Yes, it is normalizing all the way. So a lot of these things are happening automatically. We don't have to write code for this. So that's why it's important to understand these vectorizers. Clear? And there is one more interesting thing happening. Ideally, the word this, right? The word this is appearing in all the documents. So it should ideally get, its IDF should be 0, right? So this should have a 0 value here, correct? But these are non-zero values, correct? Getting it? You can see that there are non-zero values here. So why is this happening? So there is a reason for this. And that is because it is doing some kind of a smoothing. So in that version, so let's look at, so always do this TF-IDF vectorizer. We get to see the documentation, right? So there is a parameter called smooth. Control F. Smooth IDF, right? By default, this is true. So smooth IDF waits by adding 1 to document frequency as if the extra document has seen containing every term in the collection. So basically what we do is that so that we don't get 0 division, so we add 1 to that. So this is by default true. So if you actually set it to false, let's see what happens. We set it to false. Okay, we set it to false. It has not. I'm actually surprised why this is not gone to 0. Vocabulary max feature. Okay, is it using something else? Is what I'm wondering. Because what we should see here, right? This, correct? So there are 4 documents, correct? And this is appearing in every document. Maybe lowercase, it should work still, no? See. And I see. Let us check this out. And this is a bit confusing to me. Non equal to false. Should have worked. What is there? Non-parameter must be a string. Okay, none. Sorry, non equal to none. Okay, so this is 1. This is coming to be 1. Why is it coming to be 1? Is what I'm kind of trying to figure out. So, okay, this is because of this. See, So if smooth IDF equal to false, what they do is they basically add, okay, so IDF is not calculated. Okay, so IDF by default they add this 1 to this log. Okay, this was the missing thing. So it is not only this, but they also add 1 plus 1. Yeah, and because of which this is log 1 plus 1. So this will be 1. That's why this becomes 1. Getting it? So lowest value of IDF that you will get will be 1. Because of which we see this as 1. And if smooth IDF is equal to true, what happens? Okay, no problem. This is something different. That's okay. So norm equal to L2 is okay. Now you see this, and if we do smooth IDF, smooth IDF equal to true, we get slightly lower values. Sorry, equal to true, right? Equal to false, we get these values. If we do equal to true, I'll tell you what happens. The value changes a bit, right? And what is happening when smooth underscore IDF equal to true? Okay. Smooth IDF waits by adding one document to the frequency, one document to the document frequency, as if extra document was seen containing every term in the collection. Okay. So basically what we are going to do is, I'll come back to this, right? So when we have smooth IDF, there's a problem with this formula, right? So if df of t is equal to 0, what happens? You have division by 0 issue, right? So in order to prevent that division by 0 issue, what smooth IDF does is, it basically adds an extra 1. Yeah. Okay. It adds this extra document. Yeah. This is the change that I do. Okay. Done this. And because of which the values are now changing. Okay. Is this clear to everyone? There's some other parameters also that you can try. There is sublinear TF, where instead of just doing term frequency, you are basically doing 1 plus log of term frequency. Okay, so if there are some long documents, like if you have long documents, term frequency might be very high. So in order to, reduce the effect of long document, sometimes they use log of TF. Because when you do log, the values don't change that drastically. Getting? So this is very useful if you have some documents are very long, some documents are very short. So in order to have all of them on the same or in comparable scale, we add log of TF. Is this clear?
Yes, sir.
Any other questions?
Sir, can you once summarize this all TF and all once in short?
Yeah. So what exactly you want me to summarize? Yes. What do you want me to summarize exactly? A TF and IDF? You want to understand what is TF and IDF?
Exactly, like in short, like what we actually.
Okay, so let us do some calculations here. No, we can manually do calculations. So see, the purpose of taking such a short corpus is that we should be able to do manual calculation. Correct? Now let's calculate term frequency. Term frequency or TF. Let's first calculate TF, right? So TF is calculated document wise, right? So we have document number 1. Right? What is there? This is the first document, right? So you have word this, correct? What is the frequency? This is the first, and what is the document 1? Is this clear? This is the TF. Huh? So I'll just demonstrate this TF IDF calculation for this document 1. Huh? So let's do IDF calculation. Are you with me so far?
Yes, sir.
Please, it's your responsibility to tell me if you're not getting this. Huh? So now for calculating IDF. So we will calculate IDF for each of these terms, correct? So we have the term this is the first document, correct? Now what do you need to know in order to calculate IDF? How do you calculate IDF? We calculate IDF as log of n divided by document frequency of t plus 1, correct? Is this correct? So we already know
Yes.
n is equal to 4 for us, correct? Because there are 4 strings, correct? Now we calculate how many documents in which each of these term appear. Now this appears in all documents. So 1, 2, 3, and 4. All 4 documents term this appears, correct? So I'm going to write 4 here. How many documents is appears? Is appears also in all 4 documents. Getting it? So that's why you see that is and this has got exactly the same values here. So is also appears in 4 documents. How many documents the appears? The appears here, the appears here, here, here. Okay, so all 4 documents the also appears. Great. How many documents first appears? First appears in this document and this document. So 2 documents first appears. We literally do this counting, okay? Even in implementing this. How many times document appears? 1, 2. Document appears in 3 documents. Correct. So this is 3. Are you with me so far? Are you with me so far? Okay.
Yes, sir.
So we can do this calculation here, right? So let us make a dictionary. Huh? So let's say IDF stats equal to, let's make a dictionary. This appears 4 times. Is appears 4 times. The appears 4 times. First appear 2 times, document appears 3 times. Getting it? Now these are TF stats. So this is how the TF is there, right? So now let's calculate TF-IDF score for key in TF stats. Any value to TF stats. So what we are going to do is we are going to calculate. First of all, let's calculate IDF. IDF is equal to log of, let's define numdocs equal to 4. So 4 upon IDF stats of the key. This is a TF-IDF. So I think we have to do np.log to import numpy as np. Let's see if we are there. Okay, +1. We have to do +1 as well, right? +1 also. Is this clear? So let us check by doing smooth norm equal to none. Is this matching? Let's see. This is 1, this is 1, this is 1. This is matching. First is 1.51. This is not matching slightly. It is not matching. And this is 1.51, this is 1.22. We have done, okay, this should be false. Okay. Now this should match. Yeah. You see this is 1.69, this is 1.28. See, first is 1.69 and document is 1.28. And you can also see the same values here. Is this calculation clear to everyone now? Is this calculation clear?
Yes.
Is this clear? Okay. Now I do this. Let me see what happens here when I do this. I'm just trying few things here just to make sure that, yeah, okay, cool. Got it. This is correct. So there was one mistake I did in the way I explained you. I thought so. Yeah. So smooth IDF, right? Smooth IDF, I showed you that we add 1 to the denominator, but at the same time, we also add 1 to the numerator. So this is how the calculation works. So we also add 1 to the numerator when smooth IDF equal to true. So you can see it here working also. So now this is smooth IDF equal to false. You are not adding 1 here, right? So this is smooth IDF equal to false. And you can see that this is 1.28, this is 1.69, and these three are ones anyways. Right? So you can see that 1.22, 1.51. Now, okay, so we I'll not run this again. You can see that first is 1.69, document is 1.28. First is 1.69, document is 1.28. This is tallying, correct? Everyone with me on this? Everyone on this? Everyone with me on this? Cool. I see the reaction now. So now if we do, okay, so this is without smoothing. Print. Without smoothing.
Sir, why we are actually smoothing it, sir?
Yeah, the reason we are smoothing is what would happen, right? I mean, sometimes if this particular part is 0, IDF is 0, then you will encounter an error called divide by 0 error. Getting it? So we don't want to encounter that error. So we, for a safer side, we add 1. We add 1. With smoothing. Okay. Okay, so now with smoothing, you can see that this first is reduced to 1.51, is reduced to 1.22, and you can see that. So here you can do smooth IDF equal to true, and you can see that is 1.22, 1.51. Getting it? So let's do norm equal to L2. All right. Is this clear to everyone?
Okay, sir.
Awesome. Awesome. So now sky is the limit for you. Now you can do many other things. You can also do n-gram range as well, right? N-gram range. You can consider unigrams and bigrams. Same treatment will be given to unigrams and bigrams. So you can see, we now have 22 features. And they also get some values. The same kind of calculation will go for bigrams as well. Is this clear?
Yes, sir.
So play with it. Now you have the code with you, you can play with it and see what comes. So that is one thing. You can apply stop words, right? So all of those type of things you can do. Okay, is this clear to all of you?
Yes, sir.
So now what effectively we have done is we have come up with a representation. Okay. So now I will show you one more thing. How do you load a CSV file? Okay. So let us do that, and then we can stop. That's the third topic for today. All of you are quite interested, right? How do you load text data with CSV file or some file, right? CSV, TSV, whatever. So what I'm going to do is I'm going to first download the file, and for that I'm going to. So you know this UCI machine learning repository. All of you know UCI machine learning repository. You should know about this UCI machine learning repository. So UCI machine learning repository has got lots of data sets. Okay? So if you want to perform experiments, if you want data set for your machine learning experiments, there are many data sets. So we were using wine quality in our first or second week when we do end-to-end machine learning collaborate. We use wine quality prediction. Iris we use sometimes. So there are so many data sets. Right? So I'm going to download one of the data sets. There is SMS collection data set. SMS spam collection data set is there. So this SMS spam collection data set, you can read it, right? So SMS is a public data set where SMS are marked as spam and probably not spam. There are 5,574 instances. So there are so many SMSs already here. Okay. All right. So now what we are going to do is we are going to download this data set. So there is a URL that you can see here. So I'm going to copy link address. And what we will do is, there is a command called wget in Python. So I'm going to run wget command and I'm going to just paste the link, right? And run this wget. So now data gets downloaded.
Sir, is it possible to paste that link on the chat?
Sure, I'll do that. It'll be easier for all of you. Take it. Okay. Yeah, let me know once you are up to this step. Okay. And then now you can see, you can go here in collab this thing, and you can see that this is the zip file that is out here. SMS plus spam plus collection.zip. So now you need to unzip it, right? So you again write Linux command. So you do exclamation mark unzip SMS, right? So now I'm unzipping this. So now you can see that your two files, SMS collection and readme. If you open this SMS collection file, you can double click on this and you can see that there is a label at the start. Ham means it's a good SMS, spam means it's a spam SMS. So there is ham and spam, these are the labels. And they are separated by tab, character called tab. And then after this is the entire message. So we will write basically a Python code, a quick Python code, again using pandas. So we have already imported pandas, so we will not do it again. So let's say SMS data is equal to pd dot read CSV. It is of course not in CSV format, so we have to basically give the separator. You have to provide the separator. You say that sep is tab. Then there are no headers, right? So header equal to none. And you can also specify the names, right? What names do you want to give to the columns? So let's say that names is equal to the first one we want to name as label, and second is, let's say, text. Is everyone with me so far?
Yes, sir.
This is a file name, separator, There's no header. I want to give these names. So we simply run this. Okay, now there's some issue. No file or directory. This is SMS. This is not SMS spam, but it is SMS spam collection. Okay, do you see this? Simply say read underscore CSV, SMS spam collection, separator. So this is how you should organize your data. Your label should be first, then you have tab character, and then you put your text. So this is how you should organize your data if you want to do any text related activity. Okay. And see, text is of different length, right? That's why you don't want to have this at the end. So general label, you put it at the start of the file. Okay, clear? Is this clear to everyone? Cool. So I'm going to stop here for today. So you can experiment with this. Now you have code. You can play with the code, try to, open other CSV files and things like that, open data from that CSV files. I hope this is useful to you. Any comments? Is speed okay with all of you, or is it too slow for many of you? Speed is okay. Does this format suit better than what you have on the videos? Is it better format?
Yes, sir. Okay. This is the best one, because the speed and the direct interaction. This is like first time we started with a Python course.
Right, I see.
Yeah, I'm not from information technology background.
I see.
I'm
Okay.
from another background.
Okay.
For me, this is most the best one.
Okay. Awesome. I hope it's the same thing for the other guys who know Python. Okay. Any other changes that you want me to make? Let me know, suggest. Okay. We are going to stop now, and we'll meet again tomorrow. Tomorrow I'll try to do end-to-end. I'll do end-to-end demo of maybe a classification problem or something like that. And I'll also show you, a case where we have part of the data is numeric, part of the data is text. How do you process the data in that case? Okay. So I'll try to do one classification, one clustering, and then the third one is mixed data type. Okay. So let's meet tomorrow. Let's see. First, let me complete one classification one, then that composite data, and then if you have time, I'll do clustering collab, or I'll share the collab with you. You can read through it. So now the path is very clear. Now that you can take a document, you can take a corpus, you can convert that into numbers, and now the same technique would apply going forward. I'll just give you one kind of sneak peek of that so that you know how things work, because we still have some more time. So I'm taking liberty of showing you a classification collab quickly.
Sir, can you share the link of the collab file?
Yeah, I'll share the link of the collab. I'll share the link of this collab, right? The one that we used today. That's a good point. I'm going to make it available to everyone. Just a minute. Copy link, done. This is my doc. Okay, collab link. Add the collab link here. I'll also make this doc available to everyone. Share link. Okay, I'm going to paste the link to the doc here. See if you can access a doc. So this doc has the collab link at the end. Okay, so this is a whiteboard that we use today. Is it clear? Check if you can access it. I can see people on the
Thank
doc.
you, sir.
You can access it. Thanks for reminding. Now I'll show you quickly text classification, how it works. I'll just give a very quick walkthrough of this. Okay. So we are going to use basically 20 newsgroup dataset. Okay. It has got 20 classes, but we will be using only 2 classes. We will do this slowly tomorrow. Okay. But I'm just giving you heads up. So we are going to just take 2 categories of classes. And then what we are going to do is we are going to separate this data into training and test the way we do it normally. And then we have pipeline, right? In this pipeline, we are going to first use TF-IDF vectorizer with stopword equal to English and some maximum features we set because we don't want to have too many words coming in, right? So the words with maximum frequency will be chosen. And then we apply logistic regression. That's it. So this is the 3 lines of code, and then you're ready. So you have to write a pipeline construct. Whatever is the output of TF-IDF vectorizer, pipe it to logistic regression, and you basically train the model. Your model gets trained. You can get a prediction in the same way for the test data set. We can do performance evaluation. Then we will inspect the model to figure out what words are important for each of the classes. And then we'll do some hyperparameter tuning tomorrow. Okay, where we will basically play with n-gram range, maximum DF features and things like that. Okay, and we'll basically study what is the performance and things like that. Okay, so this is what we'll do tomorrow. Yes, go ahead, please. Okay, all right. So let's catch up tomorrow, and we'll meet again. Okay, we'll have fun tomorrow. So don't miss out on the session. Okay. Take care.
Excuse me, sir.
Yes, yes. Please go ahead.
So where can we get the link for this recording of the session for future reference?
I will ask our friend, my instructor, Manoj, to share that link. Okay.
Okay, okay, sir.
So
Thank you.
somebody Ravikant has already shared it. It's maybe there on YouTube. Okay. Yeah, we'll have basically 1 session tomorrow and maybe a couple of more sessions. So we'll have 4 sessions. Okay. All right.
That is
Thank
great,
you.
sir. Thank you, sir. Thank you.
Yeah.
Thank you.
Okay. Thank you very much. Take care and have great Saturday evening. Bye. Bye-bye. Okay. During the class now.